Okay. Okay, so I don't know how many of you, not all of you actually, were here like in October or so when I had the first presentation. Anyway, this is kind of a follow-up because it's a work which came from that and brought to a paper which is a joint work with Amitis, which, well, is not here, George, which is not here, and I don't know. So, I mean, I will mainly speak about generalization bounds and actually about bounds in expectation, but I will make like a quick summary just to try to see what we discussed last time. So it's already a long time ago, so I guess most of you can't remember exactly what we were saying. So I mean, just we are saying a kind of very simple framework for statistical learning. So we consider, for instance, like a supervised setting. We have some instances and we have to kind of decide which is the correct label for each of them. So, I mean, this slide is mainly to introduce notation. So, I mean, with this S is kind of the space of the samples, which are made of like M instances. So on X, which is this space of instances, we have some probability underlying measure. And then I usually denote with these capital letters like random variables and with like small letters realization of them or single elements in these sets. And we will, I mean, a very common assumption is that like the sample for your training. So the training sample is usually in supervised learning something that to each instance you have an associated correct label. So here I didn't write it explicitly why, but imagine that for each X, which is in S, you know the correct answers for that instance. And I mean, it's a common assumption that PS is like a product of the measure px for m times, but we won't actually need it every time here. So I just assume that the marginals for each sample, for each single element in the sample set xi is distributed according to this px. I mean, there will be cases in which are independent, cases in which are not. So I mean, I'm going here very fast, but because I guess that all of you know this setting, but if somebody has any trouble, please stop me. So we just consider a neural network, which is like a sort of parameterized function. So we need to tune the value of the parameters W. And to do so, we make use of the dataset S. So somehow the training consists in tuning these parameters. And in order to do so, we need to judge how good is the algorithm that we have in one moment in order to improve it somehow. And we do it through the loss function, which is a map which, given a weight and an instance, gives you a sort of penalty result. We have some, well, I should call it population loss, but risk is kind of synonym. So the population risk is the average with respect to the underlying probability on X of the loss for a given parameters. And the empirical risk, which is what we can actually in practice measure, because I mean, we cannot actually make this average in practice, is the sum, so the empirical average, if you want, on the sample that you're using for the training. So the goal is to use this to kind of decrease this loss function in order to find a good parameters. Actually, here we are focusing on the case of like the parameter doesn't have to be a deterministic function of the sample, but we kind of get with the learning process distribution over the parameters. Which is conditioned on the sample that we had. So again, the algorithm is something that given a sample S gives you actually a random variable W, which is distributed, which has some distribution that we do not like this. And if you want is like, I mean, a regular conditional distribution, if you want to be more rigorous. Now we have access, as I said, to the empirical risk, but however, we would like to control the population risk, which is the expectation on the whole instance space. And so something which is quite useful is to be able to control the gap between these two quantities. So this is what we can measure, and this is what we would like. If we know the difference, obviously, if we can bound this thing here, then summing this thing here, we have a bound on LX. And so here we will actually focus on bounds in expectation. That means we're taking the expectation both over the sample S and over the parameters W. Both of them are random variables. So we are looking at the expected value of this quantity here that I will always denote with this calligraphic G. So I hope you can read my handwriting, but if you have trouble, just stop me again. Okay, so we are interested in this thing, which are called usually generalization bounds, which are upper bounds on this quantity. So in this case, on this expected G, but it can be even on like this value here for particular that values of W and S or something like that. But here we just look at them in expectation. So there is a very rich literature about it. And the first bounds were based essentially on the complexity of the hypothesis space W. However, one of the drawbacks of this approach is like that if you want a bound which is just based on the complexity of W, it means that it must hold for any kind of algorithm which work with that hypothesis space. And so it's kind of a worst case bound in the sense that it must hold even for the worst possible algorithm. And so, I mean, it turned out that bounds of this kind were usually very loose for like hyperparameters setting like in the modern neural networks. And there was a lot of like other works coming after, and most of them was kind of try to have like algorithm dependent bounds, so something that takes into account the particular bound you're using. And a very common idea is that you want to measure the dependence between the output and the training sample. So this is what I mean we are actually interested in here, which is that they are all part of these so-called information theoretic bounds, and which are somehow linked to stability in the sense that, I mean, there is this sentence here from this paper which kind of summarizes it. The less dependent the output hypothesis is on the input, then the less you can expect overfitting, and so the better you should have generalization. I mean, just a trivial example, if you decided your algorithm, no matter what, give you the answer 3, then it give you the same error, I mean, on average on the training data sets and the whole thing, because you're always saying 3. So you're always, essentially, you're making no use of the information in the data set. So you have super good generalization, then probably terrible risk, because you have a very bad empirical risk and a very bad population risk. But anyway, you have no generalization. On the other hand, if you just want to fit all the points you have, it's likely that you will have bad generalization and overfitting. So just some notation again, and some, I mean, few definitions here. So okay, the KL divergence, Kullback-Leibler divergence, is defined like that. It's part of a larger family, which are the so-called F divergences, which are essentially kind of, I mean, divergence means that it's something that measure is a sort of, is not exactly a distance in a mathematical sense. It's not a metric, but measure how dissimilar two probability measures are. And they usually have the nice property, and it is the case for the KL, that they are 0 if and only if two measures, so nu and mu are the same. So here nu and mu are measured on some probabilistic space. And otherwise they're always strictly positive. And here, I mean, one of the defect, if you want, at least for our aim of this Kullback-Leibler divergence, is that it can actually be infinite. And it is, for instance, the case if we have that nu is not absolutely continuous with respect to mu. There are several like variational representation of KL, which are actually what are used in practice in generalization bounds, but I will not like focus on that right now. They are in the, I mean, I can reshare the old slides if you want, in which we were discussing more in detail, so the proofs and stuff. The meter information is a measure of dissimilarity between random variables, and essentially is, I mean, it's the KL between the joint low of these two variables and the product of the marginal. So it's kind of measuring how dependent they are. Clearly, if they are independent, these two measures here will be the same, and so it should be 0. Otherwise, it will be non-zero. Then we have, okay, so then subgaussianity, which is something that somehow is linked to KL if we look at the variation representation for KL. But however, what we want here is a property of random variables, which kind of tell us that we have some control on the moments of the random variables. And it is done by controlling the moment generation function, which is of this object here, which must, so imagine that Z is centered, so its expectation is 0. Then we want this quantity here to be bounded by some quadratic things in lambda for some constant psi. And I mean, if you want, if you look at the first order expansion, this is like, I mean, since the mean is 0, if we consider the mean to be 0, you will have 1 plus lambda the mean, but lambda the mean is 0 plus lambda the mean squared, and then you take the log, so you have essentially the same term, and it means that just the first two order of the expansion can control all the rest of the expansion in your third expansion here. And somehow here as well, you have several different characterization and can be linked to the entropy of the random variable, and so to the differential entropy, which is KL. And it can be seen as control on the moments and so on and so on. And it's obviously linked to Gaussianity, because with Gaussianity, you would have inequality here. So the name subgaussian comes from the fact that you start from like a Gaussian expression and then you put an inequality. Just very quickly, so this is defined for a real random variable. If we have a vector, we can speak of subgaussianity saying, okay, I want essentially that for any other vector that I can take in RQ, if I do the dot product, then I have, okay, sorry, here I forgot one piece, but so here is not xi subgaussian, xi times the norm of this p subgaussian. So here it should be taken v on the unit sphere in RQ if you want this definition. And again, instead, if you have a stochastic process, so a collection of random variables which are labeled on some set, then you can speak of subgaussianity going back to the real case and look at differences of these things, where the subgaussianity had to depend somehow on the distance. So it's controlled by the metric of the underlying label space. One more thing we will need is the Wasserstein distance, which I guess you're quite familiar with because many people had already spoken about it in these talks, and which is an optimal transport cost, essentially, in distance, in the sense that is giving you, given all the coupling between two different measures, which are like, so if you have mu and nu, and we consider, which are measured, let's say on Z, then we consider space Z times Z, and we look at all the measure on this Z times Z, which have matched on mu and nu, and we take the infimum on all this coupling, the one which minimize some sort of cost, in this case is a distance. And this gives the Wasserstein distance. It has this kind of optimal transport interpretation, in the sense that you have two piles of sands and you have to move one shape in the other. Is kind of the optimal way to move it. Actually, I didn't write it explicitly, but in the whole talk from now on, I will just consider the one Wasserstein distance, which is like essentially with one here and one here, which can be shown to be the smallest one. So given to WP and WP prime, if P prime is larger than P, then WP prime is larger than WP. So it's increasing in this index P. And so for P larger or equal to 1, so the Wasserstein 1 distance will be the smallest. And so bounds with the Wasserstein 1 distance in principle is smaller than the other ones. Okay, and the last two things, which maybe are a bit less well known to you. One is Epsilon Nets, which is like sort of, we have some space. Here we will always do everything on the hypothesis space, so I did it on W. And it's sort of discretization of the space. So it's a projection, essentially. So given a point, I'm putting it on some finite net of points on W. And such that for each point, his projection is at distance at most epsilon. So it's somehow approximating your space with a finite number of points. And then if you want, you can consider a sequence of these nets so that they become more and more, the distance is tinier and tinier, so that you're kind of converging to each points. And it's done by taking a convergence sequence to 0, which is vanishing, and it's decreasing. And then you define this sequence of nets. And I mean, for simplicity, we define this thing, we have this condition, which essentially means that like if you fix a W, then WK minus 1 can be obtained by projecting WK on the previous net. Here the WK means is the kth projection, so it's a projection with this pi k. And so it's not an essential condition. We just choose it because it makes, like, essentially because it implies this condition. Otherwise, you don't have these, and you have to write these in terms of like a sum of epsilon k and epsilon k minus 1. Okay, so I mean, this was just an introduction of the notation. We can come back if there is something you don't remember later. So now we just use all these things we just defined. And here are just, I mean, I will essentially focus on 3 very simple examples from the literature, which were discussed in the, like we discussed in October, the proofs. So here I'm not really giving proofs of them. The first one is like the first informational theoretic bounds, which of this kind, which was discussed in the literature, which is due to a paper from Russo and Zhu, and is like this mutual information bound. It assumed that all the samples in the training sample are independent, and then it assumes subgaussianity for the loss function, which must be uniform in the hypothesis. So subgaussianity with respect to the measure px for some parameter sigma. Note that, for instance, if the loss is bounded, then you have subgaussianity. Like it's not such an uncommon thing, subgaussianity. And then in this case, we have this bound here, which tell us that the absolute value of the expected generalization, it can be controlled through the mutual information, which, as we discussed earlier, it's a bit a measure of how much W and S depend from each other. So it's measuring this mutual information between the two. And then we have this scaling, which goes down as the size of the sample set goes to 0. So this is the first one. And then we have a Wasserstein bound. So, I mean, Wasserstein used the Wasserstein distance, so it needs some sort of metric on the space, because that's how you define the Wasserstein measure. And so here we don't need actually to have independence on the different samples, and the reason for that is that, I mean, we want to have this scaling 1 over square root of m, but here it's kind of quite different thing, because it comes just from the definition of the metric. So you could have our power here depending on the definition of the metric, but then you would have the Wasserstein here would change as well. So it's kind of less clear how it's going down with m. Even if there is no factor m here, it could be that the whole thing is cutting down with m, because these two distributions become more similar. But anyway, we did everything in order to have an explicit dependence of this kind. And so we define this as kind of the standard way one would do it for Euclidean things to define the distance. So we have m copies of some space, and we just use somehow Pythagorean theorem, if you want, pretending that all the increments are orthogonal. And so here we don't have anymore the subgaussianity hypothesis, we have Lipschitzianity. And again, see that, I mean, it was already true here that we had something which was uniformly true for all W and was some regularity on X, and here we have the same. So we have, for every W, we have some condition on the dependence of the loss on X, which is Lipschitzianity. And then using some variational representation, if you want, the Kantorovich, not Rubinstein formulation of the one Wasserstein distance, you can see that Lipschitzianity actually implies this kind of bound here, which again is a bound on the expected generalization error times this term here, which is measuring how far away are the measure of the sample and the measure of the sample given the particular hypothesis which has been chosen. So somehow is, again, you see that if S and W are independent, here you would just have PS and this thing would be 0. Otherwise, this thing is non-zero, and the less they are dependent, somehow the bigger it becomes. Okay, then the third bound, which is kind of the inspiration for all what will come later, is the chain mutual information bound. So it was first, I mean, one of the main problems of this mutual information is that it contains this mutual information, which is, if you remember, it's like KL between two measures, which can be actually infinite pretty easily. For instance, if you have a deterministic algorithm, this thing is infinite. So if given a particular S, the law of W is a Dirac delta, then this bound is completely trivial, because it's just the generalization is less than infinite. And so in order to address this issue, well, one way is to change the way. So to use, for instance, the Wasserstein distance, which usually is finite, as well as long as you have some nice property of your space. I mean, of your probability. And another possibility was to use the chaining method, which is a method which comes from high dimensional probability. It was originally aimed kind of controlling the supremum of Gaussian and sub-Gaussian processes, but then had a lot of other applications. And here, like instead of controlling the supremum of a process, is used somehow for controlling the average of a process, where the average is like with respect to both the labels and process. And so we have we need to use this sequence of refining nets, and we need some hypothesis. We have somehow to use the metric of the space. So previously we use it in the directly with the vast system distance, if you want. And here, I mean, we need to use the metric on the hypothesis space. And to do it, we need this. So that's why we have this refining sequence of nets, because they're kind of consider how dependent two hypotheses are from each other, like how far they are in the space from each other. And then we consider that the process is sub-Gaussian. So if you remember, it means that if we take two differences, so LW and LW prime, then the difference between these two things must be sub-Gaussian with a parameter which go as the distance between W and W prime. And in this case, we kind of find again this term here, but this time we have a sum. This is, sorry, it's not an M, it's a K. So we have a sum for all the different discretizations that we have in our sequence of refining nets. And this WK is the projection of the kth net. But I mean, I will discuss a bit further later about what it is. So anyway, we have these three bounds so far. And if you look at the literature, essentially there are plenty of bounds in these forms with a lot of variance and stuff like that, and very few bounds. Actually, when we started working on this, there was just this paper which was actually doing chain generalization bounds, and then just 3 days before we submitted it, there came another paper finding another bound. But anyway, so essentially, and both of them were focusing on this mutual information. So the other paper were just using a variant of the mutual information, but for the single, I mean, anyway. But so the question is, can we actually do it for other kind of bounds? For instance, can we have a chain version of the vasticity bound? Or I mean, can we do it for, in principle, any kind of bounds? Can we have a chain version? I mean, here as spoiler, the answer is somehow yes. At least there is a sort of duality. And the other question is like, which one is the tightest? So in the paper which introduced this chain mutual information bound, the motivation was that if you take, for instance, some deterministic algorithm, this thing can be finite, while the other is infinite. So there are cases in which for sure it's tighter. But what in the general case? So we can, if we can have this sort of duality, can we sometimes say we are sure that the chain bounds is tighter or not, or this kind of thing? So here, just to, I mean, spotlight what will come later. So here are somehow, so this is the mutual information bound, and this is kind of the chain mutual information bound, which is like a reformulation with this sum over all the different scaling. And again, we can have something very similar, because we take the Wasserstein bound and we can have a bound in this form, which again is having here, if you see, I don't know how much is readable, but there is a K here, which means that we are looking at the PS condition on WK instead of W. And so, okay. So in order to establish this duality, the first thing we do is kind of to try to find a general framework in which we can fit all together the previous bounds. I mean, this is something quite trivial if you want, but which is kind of useful to state the thing in general. And so the thing that I kind of mentioned earlier is that for all these generalization bound we had, at least for the first two, so the unchained bounds, it's very common to have an assumption which is uniform in the hypothesis space, so in W, of regularity with respect to X. So we had sub-Gaussianity with respect to X, uniform in W for the mutual information, and the Lipschitzianity with respect to X, uniform in W for the Wasserstein. And the key idea for all these information theoretic bounds is that we can rewrite the generalization in this way. So essentially, as the difference, so this L should be a calligraphic L, sorry about that, the difference of the same object with respect to the different laws, which are the product of the marginals and the joint low of the hypothesis and the sample. And essentially, I mean, this is just because if you rewrite the population risk, it's just, I mean, it's easy to see that it can just be written this way, and this is just the expectation under the product of the two marginals. So now, I mean, we just defined this concept here, which, I mean, is kind of targeting the bounds that we want to get. So let's keep it general. We consider some space, I mean, a Polish space actually, which is required to have some metric. And we look at the space of probabilities measure on the space, and we consider some function which can be, for instance, the associated distance or some probability divergence or whatever. I mean, it needs to be measured somehow, but we don't discuss it here, which just takes two probability measure and gives you a positive number. And hopefully it will have something nice, some nice property. So if you give twice the same thing, it will be 0, or otherwise it's positive or something like that. Anyway. And then given a function f, which goes from 0 to r, we say that it has regularity Rd if it's with respect to some measure. So I mean, this regularity is kind of mu dependent. So you fix mu and then you define the function which are regular with respect to mu. So it must be, first of all, integral with respect to mu, so finite integral of the expected value of the absolute value. And then you need essentially to control this thing. So you want to control the difference of the expectation under this mu and the expectation with respect to any other measure mu which satisfies some properties in terms of this distance d between measures that you just defined. Okay, I didn't write it here, but you can kind of define the regularity for like vector valued function as well. And you can do it in a similar way to what we did with subgaussianity. So you take the inner product between the value of your function and any fixed vector, and then you ask that this is a regular function. I mean, this is a real function, this inner product, and you ask that it has regularity with xi, which again is xi times the norm of the vector you have fixed. Okay. So now, I mean, why do we want these? Essentially because if we can control this kind of object, hopefully you can control this kind of objects because they're very similar somehow. And so indeed, the idea is the following. So if we consider that the function that maps to your training sample, the empirical risk, and if you assume that it has some regularity Rd xi with respect to the low PS, which is the low with which you draw your sample, then you can have this kind of generalization bound here. And I mean, this is kind of in the form more or less of most of information theoretic bounds. I mean, at least of many information theoretic bounds in the literature. And so, and the proof is actually, I mean, trivial. The main point will be then to show that this mapping here has this sort of regularity, because once you have it, just by definition, I mean, okay, there's a few technicalities, but then you just apply the regularity to this object here, which was, again, this definition here, of G. And you do it essentially, so for each W, you apply it with the fixed W. So your PS given the fixed W, and here is PS. And this is just a definition of the regularity. And then you take the expectation of, with respect to W of this object here, you just use Jensen's inequality to bring out the absolute value, and you just find this kind of thing here. Okay, so I mean, how we recover the previous result? Well, one thing is that, and essentially then it goes back to the proof that are in the literature of these two results. So if you have something which is sigma sub-Gaussian with respect to this mu, and here you see why we need the particular mu to be fixed here, because like something can be sub-Gaussian with respect to a measure and not to another in general. So then you have that with this choice of D, you have this regularity, and if you take Lipschitzianity, you have that with this choice of D, which is the associated instance, you have regularity. And so this result here essentially brings you back the vast system bound, and actually a strengthened form of the mutual information bound, because you could take this square root inside here. I can play it a bit with that. And okay, so essentially we have recovered the two previous results. And then, I mean, there are other results, like, for instance, if you take something which has the variance with respect to mu bounded by 1, then you can have regularity with some function of the chi-square divergence, or you can have all these kind of things. Or like alpha divergence, in which I think you will speak about next week. So it's some kind of control of the moments or stuff like that. Now we want to, I mean, we cannot fit in this framework the chain bound, because it didn't have an hypothesis like this. It didn't have something like we have a uniform hypothesis of regularity or something. That is something more complicated. You need to control the differences somehow. You have to have some sort of uniform regularity on difference between LW and LW prime. And so okay, so somehow now instead of just controlling the regularity of this L, we need to control the regularity of this object here. And indeed, I mean, it turns out that it's possible. It's just that the statements are a bit long. So it's much nicer if things are regular enough, so that instead of looking at the difference, we can just focus on the gradient, which is somehow controlling the difference by integrating it. So now, I mean, we just give some assumptions, which are essentially the one required for the gradients. They can be weakened somehow. If you don't assume, for instance, differentiability, can still deal with the differences. And the gradient then asks you to require convexity to, because you want segments or stuff like that. But anyway, so I mean, your space W need to be, well, I didn't mention it explicitly earlier, but when you do your chaining thing, you need your space to be bounded, at least for this version of the chain. There are then other more general version of chaining we don't, but we always focus on the case in which the hypothesis space needs to be bounded in order to do the chain. So that you have some sort of diameters, which gives you the larger scale epsilon 0, and then you take like smaller and smaller scales. So essentially, these are just, I mean, closeness here is just to have Polish spaces, just technically, it's not really needed in practice. Then, okay, we want differentiability and stuff like that for the loss function in W, so that we can look at its gradient. And then we want some boundedness, essentially, because we want to be able to exchange integrals without caring too much about what we're doing. But I mean, it's not like they you just care that they're bounded. The bound will not appear in the generalization bound. So the fact that they're bounded by 3 or 3,000 doesn't really matter for what we want to do. Okay, now we have a sort of dual of theorem 1. So we have similar assumption, but now we have that instead of looking at the regularity of L, we look at the regularity of its gradient with respect to W, again with the same definition of the irregularity, and then we have a bound in this form, so it's something very similar to what we had earlier. So if we remove this sum here and we remove the k, we have just the bound we had earlier. But now we introduce this sum, and we introduce the fact that instead of having the distance d between ps and ps given w, we have ps and ps given wk. And the proof is now a bit more technical, but it follows essentially the standard chaining techniques. And so the first idea is that you write, I mean, so LSW, you can write it with a sort of telescopic sum. So you're just, I mean, you start from W0 and then you write all the differences, since this WK tends to W, and then you have all the continuity you want. And then, so I mean, if you fix the, okay, then I mean, you take the expectation, and you will need to control essentially the expectation of this sum here, because the expectation here will be 0, and you control them via the regularity. So you can always, again, so here is a regularity of a gradient, so of some vector valued function. Yes. For the slide or the whole presentation? No, the space W is complex.
Okay, so what you need to, you want to control the difference, and for you, like you control the gradient, but you don't use the convexity inequality.
No, I mean, the reason I have a convex space is because I need to control differences, right? And essentially, so if I control the gradient, I can integrate from one point to the other. I integrate the gradient, and I want to integrate on the segment in order not to deal with Riemann manifolds, which I mean still would bring the same result probably, but you need to introduce the metric tensor and everything, so it makes just a mess. So that's the reason for convexity. That's the only reason for convexity. So if you look at the proof, indeed, every time you need to control these differences here with regularity of the gradient, essentially have an integral, and then you control the integrand and so on. So here you say, I mean, in the theorem 1, you had this thing here, which was this function here. The empirical risk is a regular function uniformly in W of S. And here we have that the gradient of this thing with respect to W is regular. Okay. And then, I mean, so you write this kind of telescopic sum. And so essentially, which means that you just need to consider this difference between subsequent projections, which are so getting closer and closer. And you control them through the gradient, like integrating essentially the gradient between WK and WK minus 1. So when you will kind of eventually split these integrals, so it becomes that the integral of the gradient between these 2 points will be controlled by the distance of the 2 points times the integral of the gradient. I mean, the difference will be controlled by these, and the gradient is such that it can be controlled with this irregularity, if you want. And again, so the gradient is a vector valued function, which means that the regularity is given by, like, given essentially the direction in which I go is given by the projection in that direction, which is essentially, I mean, if you want reason, you get the final formula here. I didn't write too many details here because I don't want just to do a whole proof, but it's quite simple actually, the final idea. And actually, I mean, the way you prove it is that you prove it actually for the differences. And then you prove that these regularity assumptions here ensure that having the regularity of this gradient implies that all the differences are regular with this thing here. And then again, you conclude just by taking the expectation. So here you do it for a fixed value of W, and then you take the expectation on W and you get the formula here. So now we go to the 2 bounds we like the most, which are the vastest and image information 1. And so we have that. So if we have this assumption on the gradient, we get exactly the bounds that we wanted earlier. And if we have Lipschitzian, we get some other bounds, which is new if you want, and which has this Basisian distance between PS and PSW given WK. Now, if you look at the hypothesis here, sorry. So it was different. You didn't have any assumption on the gradient, essentially, because you had this subgaussianity of the process. But the whole thing is that under this assumption star, okay, you have that it's actually equivalent. So having a gradient which is a sigma psi subgaussian is actually equivalent to have the psi subgaussian process. So this is exactly equivalent under stricter assumptions. So you need this convexity of the space, this C1 of the, but to the previous statement from the literature. Okay, so we have seen that somehow we have this duality between theorem 1 and theorem 2. I will come to that a bit later again, just to summarize it. But now there is the question, which one is actually the tightest? And I mean, in general, there is not an answer. So it's really like depending on case-by-case scenario. But one thing you can always notice is that actually somehow the chain bound requires stronger assumption. This is in the sense that, I mean, it might be that you have that this gradient is regular, but L is not regular, but you can always kind of modify it to find a regular L. So if you have that this thing has regularity RD, then you know that you can define essentially a modification. So you just take the difference with a fixed point, for instance, this W0. And these will have regularity RT actually. The function itself and not the gradient. But then you can see that it's not an R proof, it's just like essentially two lines proof or so. So it's nothing very fancy. It's just following the two definitions. You can see that it's the same. And since this is the generalization with the risk is actually equal to generalization with this, because the generalization is just the difference between this and its expectation. So this is canceling in the two terms. And so essentially every time you can get a chain bound like that, you can actually have a non-chain bound which have this factor epsilon 0 in front of it. So somehow, in this sense, the hypotheses are kind of stronger for the chain one, because you can always recover while the other is not true. So you can have cases in which you have just this regularity and you cannot actually achieve the other by such a simple modification of the velocity. On the other hand, so this is somehow telling us, well, it's kind of, for now, the unchained version is better somehow because it's easier to get it. On the other hand, you have that the conditioning can be actually helpful. So it was already clear on the mutual information because we had that one was infinity and the other could be finite. And here the idea is that in general, if this D, which was this kind of divergent, dissimilarity measure between probability is a convex function of the probabilities, of the probability measures, then you have that. So if you take tinier and tinier steps in your nets, this is an increasing function. So if we start from some very small value, and then as you approach something which is like, ideally, if you want for k equal infinity, wk is equal to w. It's not exactly true, but imagine something like that. But so essentially gives you this, that for each k you have that these quantity here, which are the thing which appears in the chain bounds, are smaller than the one which appears in the unchained one. And then these things are actually increasing. And the convexity of this D happens actually in the phase of interest. The KL divergence is a convex function. Actually, if you look the regularity, you had the square root of KL, which is not convex. But the way you prove it is actually to using like KL and then taking a square root. So essentially, in the way you prove it, you can show that this is always true for that bound as well, essentially with the mutual information. Or if you want, no, okay, sorry. The bound had the mutual information, so you were taking out the square root from D to outside the expectation in the mutual information bound. So the mutual information bound is not exactly in this form because this form will be the square root of KL, but then you're taking out the square root. Yeah, which is concave, so the square root of the expectation is larger than the expectation square root. So somehow taking out the square root then gives you a form which here has KL, which is a convex function. So again, you have this property for the mutual information. Anyway, so this whole thing is to say that if you know that up to some scale, so up to some k star, all these terms are very small, which is kind of possible, then you will have something that increases, okay, but is always bounded by this term here. So you would have that this sum here, which is what appears in your chain bound, can be rewritten actually. Let's say that up to this k star, every contribution is negligible. So it would be just the sum of k, which is larger than k star of this term here, times this term here, which can all be controlled by these. And these can actually be much smaller than epsilon 0. And so you would find that the chain bound is actually smaller than epsilon 0, much smaller can be actually than epsilon 0, this term, which was the, in principle, worst case scenario you can get for the chain one. So it can be that the chain one is still much tighter than this. It's not always true, but there are situations in which. So in general, we cannot say which one is the tightest, but there are situations, and this is especially true, we will see now, if we have one point under which the whole W is very concentrated, then, it's not at all informative to know that we had exactly that WK chosen, because all the other WK are chosen with super small probability up to some scale in which we are in this concentrated region. And so just to see it with a very simple example, you consider a one-dimensional case here. Let's say the sample is just one element. So instead of writing S, we write X. It's a very trivial thing, but just to give an idea of what's happening. And so, so let's fix some K star in this way so that, we have, this is -1, 1 is your space W, and this is how you choose your points WK, okay? So you're kind of taking smaller and smaller steps here. And then you choose an algorithm that minimizes this loss here, so that given X picks W equal X. It's a deterministic algorithm. So for instance, the mutual information bound for this would be infinite because it's deterministic. And now you say that the whole thing is concentrating in some small neighborhood of 0, which is from minus delta to delta, where delta is equal to these 2 minus K star. Now up to K star, essentially you have, so you have that with probability 1, the W will be in here because X is uniformly distributed on this small interval. So until K star, I mean, you have that with probability 1, WK is equal to this point, and probability 0, you have this thing here. So essentially means that X and WK are independent. Do you see that? Because it's just a constant function, WK, no matter what's the X, because the X is always here, so WK is always this point here. This means that up to W square, up to K star, all these terms are indeed 0. And so we just have this sum here. And this actually brings, I mean, you can compute everything explicitly in this example. So you would get that the bound with the unchained bound with Wasserstein is scaling like theta for theta going to 0, while the true generalization, which can be easily computed, is scaling as theta squared. And the chain Wasserstein bound has Wolf's constant here, but the scaling is correct. So it's going as theta squared. So for very small theta, actually this, I mean, the duration between these two is going to infinity. Now, one important point is that this works very well if you have one single point around which you have this very strong concentration. Because if you have already 2 points, I mean, actually things break down, because then you can have that it can be very informative to know under which point you are. And you don't have any more an argument like with probability 1, you're just, all your points are here, but you still have like at least 2 points to be chosen. So in general, you cannot say, and again, it's really kind of case by case dependent, and there is not such an, I mean, this was kind of the easy example to say, to show that the chain bound can be much tighter, but in general it cannot be. So we had another example, which is kind of higher dimensional, in which you had like a strip of points, a tiny line of points, which is a very high concentration. So in principle, even distant points can have very high concentration. But there, when the thing becomes super high dimensional, then again the ration of the two bounds show that the chain Wasserstein can be much smaller than the standard one. But it's kind of less intuitive compared to this, because you don't have anymore this very strong concentration around a single point. And anyway, in that case, like both bounds do not capture very closely the behavior. So you have that G is actually always much smaller than both, and then the second is like G is much smaller than the chained one, which is much smaller than the Wasserstein one. Anyway, now, okay, just, I mean, very quickly, just to say, so far we just focus on these kind of informational theoretic bounds, but the same idea of like chaining can actually be applied to other contexts. So it's not part of the general framework, so it doesn't fit like that exactly, but the methods are essentially the same. Even if, so this is like a Pac-Bayesian bound. I'm not now speaking on Pac-Bayes, just to give an idea that other things can be done. Essentially, these are other generalization bounds. They're not bounds in expectation, but they hold with high probability for a stochastic network. And they need some sort of pri, which is not really a Bayesian pri, but anyway. So anyway, this is kind of the form. So this G is like the generalization is not without taking the expectation. Taking the expectation just with respect to W, but not with S. S is fixed and is random, and these bounds hold with probability, high probability for S, essentially. And you have the KL between this, this thing and a fixed prior that then you fix. And the difference here, so is that, okay, you can get a bound in this form where you have WK instead of W. The good thing is that, again, this for a deterministic algorithm is infinite. This is not. I mean, it can be finite. Another thing is that for peg-based, a very, very standard hypothesis. There are more general things, but it's a very standard thing, is that you need the loss to be bounded, which is not truly the case here. I mean, it is somehow, because you have the space is bounded and the gradient is bounded, so you need the loss to be bounded. But can be bounded by much larger constant, and the constant doesn't directly appear in it, but it's the grad, so it's kind of needs to be Lipschitz somehow. And then you need, I mean, a huge amount of hyperparameters then can actually be tuned up here, which is not a super good thing, but I mean, still these can be like finite when this is infinite in some cases, so it can be interesting. And we didn't explore it too much from like toy model or experiments, but I don't know, might be interesting in the future. And okay, so another thing is, like earlier we had something which are called in the backward channel in information theoretical literature, which is you look like the forward channel would be you have S and you take W given S. So you look at the distribution of PW and PW given S and compare them, which is what is happening here. So this is a bound with the forward channel, if you want. And so here you're looking at PWK given S with respect to some PWK. All the previous bound were the backward channel. So there was PS given WK, which kind of makes more sense when you look at least at the vast state distance, because doing the chaining here with the vast state distance, I don't think makes very much sense. Maybe yes, but I don't know. It was more natural to do the other channel, but it might be interesting in the future to look at this channel too for the information theory bounds. Okay, so essentially we are done. This is just a kind of summary of what we established, which is we have this sort of duality. So if we have bound based on a uniform regularity for the empirical, yes. Yeah. Where is he? Is it on the chat? Or?
Oh, is that me?
Oh, okay.
Yeah, I didn't really, I can't really visualize or make sense of this backwards channel type bound. Is there like a particular advantage aside from it being more conducive to the chaining technique? Is there a particular advantage to considering backwards channel, whatever you called it, sort of bounds as opposed to the forward one?
I mean, I guess it just gives you, usually there is a sort of duality on which space you put regularity. So for instance, the original vast state bound here is a backward channel because it's looking at the vast state distance between two space and needs as assumption the Lipschitzianity of L with respect to X. If here you look at L, which is a Lipschitz with respect to W, then you have a forward channel. So in the literature, kind of both. So I would say they're kind of dual one to the other, and they require different assumptions. So there is not one which is always better than the other because one can work while the other doesn't. Chaining on W, I think is more, makes more sense with this backward thing because you're kind of inserting a metric structure on W, and so you want to control, for instance, with Wasserstein, the metric on X in order to control them both. And it doesn't really make sense to have both a chaining which control your metric on W and the Lipschitzianity which already control the metric on W. That's what I was trying to do at first, but I couldn't really find a smart way to exploit both things. Whilst for instance, the Pag-Bayesian bound, you have the KL, which is not affected by the metric at all. So in that case, it can make sense to control the metric on W in a sense. Sorry, on X instead of on W with the chaining, because you had no control in principle on the metric on X. But yeah, I don't know, maybe it's probably less intuitive. Yeah, indeed it is but eventually, like for instance, for the mutual information bound, you can see it in both ways because the mutual information is symmetric. So you can actually replace this hypothesis here with subgaussianity with respect to W for every X, and then you don't have the factor 1 over M, but you get the same thing. And yeah, one more thing is like, so if you look at the forward bound here, so the one with the representativity on W, you don't get this factor square root of m, because then you cannot exploit this kind of metric structure here, because W is not like a product space usually in this kind. But yeah, in principle, I do agree that they are more intuitive, like, because the idea is like I have a sample, and then I got parameter depending on my sample. So I want to look at the difference between knowing nothing and knowing the sample of my parameters. But this is just kind of the dual point of view. Like, let's go back and like, what was my distribution PS if I don't know what actually has been chosen? And once I know what has been chosen, I mean, is there some PS with some sample which is very likely to have been chosen? Like, if there was just one sample that would have gave me that particular and super extreme hypothesis, then it's very likely I'm more overfitting. Like, I just got that particular sample. If, on the other hand, many samples were likely to bring that hypothesis, then it's kind of, you don't think that you're overfitting. Like, that's the kind of intuition behind why generalization bound can be backward, is kind of this.
And have you seen any sort of, with the mutual information bounds, the forward channel bounds, there were attempts to like study them, for example, study the generalization of SGD or SGLD. Have you seen backwards channel bounds being used for anything similar?
I don't know. I'm not like I'm aware of that literature. I'm not super familiar with it. At least I didn't read it very recently. Probably Badger know much more about it, but
no, I don't think I can answer this question.
Okay, but you cannot answer the question, so so I'm not aware, honestly. But there might be something with this Wasserstein band, actually. I know there is some analysis of SGD via Wasserstein band, but I cannot say if this one of the forward band. Perhaps you know, but I don't. So I don't have an answer. That's my answer.
Thanks.
Sorry. Okay, is it all right, or you have other questions? Okay. So again, I mean, just to summarize everything, we have this unchained bound, which is the regularity of L. This chain bound is the regularity of the gradient with respect to W. Given you on the previous thing, I guess that no, nothing. Okay. So then another thing that could be done in practice is kind of doing the chaining on X, which I don't know how much is feasible, but so looking at like the gradient of X here and stuff like that, that might be an interesting direction, but we didn't really try to do it. And okay, so here the bound is in this form. I forgot that to close the bracket. And here you have the chain version of it, which is just the same, but with this sum over all the different scaling. So it's a kind of multi-scale bound. Okay, here's just to give some example that there are other examples which fit in the framework. So it's kind of, I mean, perhaps it's not very meaningful, but it's just to give an idea that other bounds, many of them are from the literature, and for each of them we can kind of build a new chain generalization bounds. So this is the other paper I mentioned that is just a few weeks before we published there was this coming, I mean, our archive, there was this coming out, which again was something related to mutual information. So there is this this integrated mutual information is called. So you're looking with the mutual information between each element in the sample and W. But yeah, as far as I am aware, there was nothing like with fastest and distance and chaining so far. I mean, here there is something with the P power divergence, which I guess is related to Camellia's alpha divergence too. Here is the thing I was mentioning about chi-squared. And then we can recover all these kind of single, like this integrated mutual information, and we can recover something else, which are these super sample setting in which you kind of, I mean, they come from a paper from Steken, and I mean from this paper here from Steken and Zacchintino, sorry. in which you kind of consider on a bigger sample, and then you want to recognize which of the element of the bigger sample were in the sample that you use for the training. And here as well, it was a way to make finite the mutual information bound. And we kind of showed that it's possible to make a chained version of these things as well. Then we didn't discuss it with the example or stuff like that, but I mean, again, the previous discussion is kind of general. So every time you have this super concentration around a single point, then you know that for sure you will have a tighter bound with a chain. Okay, so just, I mean, these are some extensions we mentioned in paper. We didn't develop much around it. One is, well, what I said before, so this is kind of fully developed, is that you can have weaker hypotheses. So we can just ask the compactness for W. You can just ask for continuity. Actually, these two could probably be weakened, but so the original assumption for the mutual information bound is with separability. The proof they give, according to me, is wrong in the sense that they make a claim that separability implies something that separability does not imply, but separability plus subgaussianity should imply it. But we couldn't make it general for the whole thing, because then for the whole, so essentially separability of the process. And here we just ask the process to be almost surely continuous, which is something which implies separability. So it's stronger, but makes the proofs much simpler. It might be that just asking separability of the stochastic process is enough, but I'm not sure at all. And yeah, I spent a bit of time on it, but I couldn't figure it out. Okay, and then you don't need boundedness, like complete boundedness, but just sort of boundedness in expectation. And other thing is that, like, so far all the bounds had this uniform regularity on W, which can be pretty strong assumption actually. But you can kind of generalize them, and like asking a regularity which depends on each different W, and then instead of having like the standard bounds that like something, sorry, like this kind of expectation here. I mean, you will have some exponent here because you want to use some sort of Holder inequality. So you want to be able to control some moment of this W, sorry, psi W when you take the expectation with respect to W, and then you get some sort of variant of the previous bounds. Okay, so other thing that could be done in the future, I don't know, but like one is stochastic chaining. Stochastic chaining, I mean, it's the paper I was mentioning earlier. So they were actually, the main topic was not to do a new chain bound, but was to show that there was these stochastic chaining techniques, which essentially means I take my nets not to have a fixed deterministic scale, but to have the distance between WK minus 1, or NW, if you want, is undividable, and I want to have it controlled in expectation, because it's just what I actually need in the whole proofs. There they change a bit the assumption, and actually they don't say it, but they make a quite strong assumptions on how things work in practice. But yeah, it might be an interesting direction, but there is some technical stuff which I think would need to be done to do it properly, for our case at least. Then another question is, okay, we spoke about regularity, but like for instance, we say that if it's Lipschitz, then it has regularity with respect to W1, Vasily 1. Like, can we say more? Like, actually, well, I mean, you can show that Lipschitz is necessary and sufficient somehow, at least on the support of your measure. But what about other P versus A distances, so versus A2 and so on? Can we actually characterize these class of functions? It's trickier than I thought. I'm trying a bit, but it's tricky. Then another thing is, like, well, to go back a bit to what you were saying, so try to use it with SGD or these kind of things. So try to dig a bit in that literature and see if something can be done with chaining as well. Especially because most of those papers, at least the one which use the mutual information chaining, they finish saying, oh, it might be interesting to do with the mutual information chaining. Sorry, they use the mutual information bound. They usually conclude by saying that other possible things could be try to doing it with chaining and mutual information. So maybe it could be done, and maybe it could be done even for buses. I don't know. Another thing is like kind of one of the failure of the whole chaining thing is that if you have concentration around a point, it might actually be very cool to bound. So can we do better in that direction? I don't know. I don't have many idea about it, but it might be interesting to look at that. So just to very quickly conclude, so if I took actually longer than I thought. We have this duality, which was the whole discussion we had. In general, you cannot decide which one is the tightest, but kind of if we have very much concentration in some very small region, then you have a benefit in chaining. And then again, I mean, this assumption can be weakened in general. So you can kind of, I mean, the main thing is that you don't need this uniform regularity, and then you don't need all the regularity for the functions. So thank you. Here are some some references. It's, I mean, these are really just few, and are essentially all the things that we mentioned. In this book by Van Halen, there is a pretty nice introduction to chaining. It's essentially all my knowledge about chaining mostly comes from there. At least in his original versions of Suprema of random processes. These two papers were the first ones to introduce the mutual information bound. This one, the one introducing the chaining mutual information. This one was the first one with this backward Wasserstein bound, which actually came before the forward Wasserstein bound. And here, okay, so I mean, these are just the single, I mean, the disintegrated mutual information bound and the one with the super sample that I mentioned there. So yeah, that's it. If you have any questions.
Thank you, Eugenio.
One question.
Yeah. Okay.
Yes, thank you.
Thank you, Eugenio.
Okay.